We're going to focus on three main areas related to the challenge of water production in this session. The first will be, fundamentals of water production, the issues this may cause, and why we need to manage it overall. We'll take a little trip then into the main techniques that we use to resolve water entry, some of their limitations, and how we might be able to improve on this, which is the main subject of this session today. And we'll explore that solution through case studies based on work that we've performed to really demonstrate how what we describe as maybe video-assisted production logging can really help improve on decision making and hopefully deliver the information you need to make the right decisions at the right time. Before we get there, I just wanted to stress as well that we're not all about water production here at EV. That's one of many applications that we service. And before we get into the main body of the presentation, I just wanted to make a nod to all of the other types of operations that we run. And this slide here is really just saying that we operate on any mode of conveyance, whether that's on jointed pipe, it could be drill pipe or a snubbing unit, electric wireline, coiled tubing, or slick line. Any type of conveyance, we have a video system that will provide high quality images to suit any application. And these applications can be very wide ranging, from evaluation services like corrosion, water, or production related, to more mechanical services like wellhead inspections, trees, valves, even valve reactivation, scale removal, perhaps pre and post scale treatment, and a range of activities relating to keeping the wells healthy or to help abandon them and make them safe for long-term suspension. As you can see here, in the last 12 months, we've performed over 900 successful surveys globally, which makes us the #1 video provider. And you can see a different view of the applications that we're involved in, everything from diagnosing wellbore restrictions and helping to overcome them, through removing fish that may be stuck in the well and preventing safe production, and all the way down here to what is actually today's topic, a small but emerging subject of using video to help manage water production. But what I wanted to also stress is that the video services that we provide are a strong enabler for healthy, productive wells. And if you look here at this final pie chart we've got here on the right-hand side, you can see that over 90% of what we do relates to producing wells and helping to maintain production and keep them healthy for longer, with the remaining 8% relating to plug and abandonment services that we provide in a range of locations globally. So that was just a brief introduction before we move on to the challenge of water production. And to set the scene, I'm going to use some real-world data, some macroscopic data that I've borrowed from the UK oil and gas sector. Apologies, this may not be relevant to all of you that are listening out there in the Western Hemisphere, over in the US, Canada, or South America. But I think when we look at the data, we'll recognize some familiar trends, because I think although every well and every field is slightly unique, there are some macroscopic trends that will be similar from one location to the next. So as I said, this data has been taken from the UK Oil and Gas Authority, who regulate, influence and promote the UK oil and gas industry in order to maximize economic recovery from the region. And this is placed into the public domain, so we can share that openly with you today. And to help understand the impact of produced water, I want to take us through two charts that we can use to look at the impact of this across the life of a well, or indeed the life of a field. The first chart is a relatively simple plot of the produced fluids by volume on the vertical axis against time on the horizontal axis. And you can see this goes all the way back to the starts of records in the mid-70s. And I've just cut it short at the end of the last full calendar year, at the end of 2019. And you can see by the key underneath that we're looking at the produced oil, the associated gas coming with the oil, dry gas from gas wells, and the water production overall. Now, as you can see, right back at the early part of the North Sea and UK production history, we had predominantly oil and gas being produced. The hydrocarbon was essentially virgin, and there was very limited amounts of water in the early years. But it didn't take long before that started to accumulate and become a major part of everyday life. And as we come up to roughly around the new millennium, we see a peak in production and then a tail off until roughly the middle of the tens. And in recent years, actually some very positive signs from the efforts of the Oil and Gas Authority in promoting efficiency and recovery of production in the North Sea itself. But why is this relevant, and why do I think there's some familiar trends? Well, again, that water breakthrough and the increased presence of produced water is something that will happen over time in the majority of fields. It may not be an absolute inevitability, but it's quite likely that as we reduce the hydrocarbons and deplete the reservoirs, it's likely that we'll bring water in from the surrounding areas as we deplete those zones. And today, the average water content from the total North Sea production is sitting somewhere around 70%. So for every 10 barrels that we produce, 7 of those 10 are now water, with only 3 being hydrocarbon. The significance of that is really twofold initially. The main drivers are economic. That first of all, every barrel of water that we're producing could have been a barrel of oil. We have a limited amount of recovery that we can make at any given time. The production is limited by the pressure drive or secondary lifting mechanisms, and the volume is fixed. It is simply the capacity of the well to lift that and carry it along its transport stream. So if we can reduce the amount of water, we can effectively draw down harder on the hydrocarbon-bearing reserves. And that means greater productivity and increased peak performance. On the other side, once we've got this water, we've got to deal with it. We've got to treat it and dispose of it properly. Sadly, this is not Evian and won't be sold for several dollars a bottle on a restaurant table, although other brands are available. So having looked at this, I'm sure there will be familiarities and some similar trends in the region that you're in. It would be really good to discuss if there are any major disparities or any things that have occurred that have changed the water production trends in your region. Or better still, if you'd like, drop me a note after the event with data that I can access for your region, and we can replot this and tailor the discussion to your specific location. But the second chart I'd like to look at is a bit of a deeper dive into some of this information. The chart on the right-hand side is the top 20 oil producers from the United Kingdom. And at first, it may appear random that we've got bars of different heights in different locations. But that's not actually true. This has been sorted by rank of oil production from each field. So you can see here on the left-hand side, this is the #1 oil producing field in the UK continental sector. And then right here on the right-hand side is the 20th highest producing or highest oil contributing field in the UK. So it's quite a mixture. But what I'd like to do is really draw on 2 particular groups and discuss the issues and perhaps the solutions involved in managing water in each of these cases. So the first group is actually our top 2 wells. Buzzard, the top producing field, whose first oil was produced in 2007. So in relative terms, this is a fairly new field within a quite mature basin. So it's not a surprise that it's got higher oil contributions than here, which may date back a lot longer. The second highest oil producing field, Schiehallion, although that was first producing oil in 1998, the field actually underwent a significant redevelopment in 2013 and was brought back online in 2017. So effectively, there's a lot of new reserves and new production here again, having been revamped. And interestingly, the redevelopment was actually made primarily to cope with the increased water production from this field as time went on. So in these 2 scenarios where you have high oil production and relatively low water by comparison, you're probably looking to find significant changes in water over time and act on a well-to-well basis, case-by-case basis. And you probably won't act until the impact is significant enough that maybe you're losing primary pressure drive and you're having to think about artificial lift. So perhaps then you could look at going in and eliminating water at source. The challenge there is that because the oil production is so high, the risk you take in an incorrect decision, potentially isolating some of those oil-bearing zones, is relatively high. So you'll want to have a system that is robust and gives you the most comprehensive answer so that when you do act, it is the right action first time. Our second group is actually number 9 and 10 in the top 10. And it's incredible to think of this, but actually these two fields are producing in excess of 90% water, which is incredible really, but it shows that even very mature fields with high water content can be made to be productive and profitable if managed very carefully. And the story of these two fields is quite relevant, so we thought we'd just take a little trip through that as well. The Forties field is one of the first major oil and gas discoveries in the United Kingdom. It was first brought online in 1975, but from the very outset, production was driven and supported by peripheral water injection. So this field has always had an element of produced water as we started to sweep and flood the hydrocarbon through the sands and to the producing wells. Captain, on the other hand, although that was brought online similar time to Schiehallion around 1997, this field was actually an early adopter of polymerized water enhanced oil recovery. So this field started a program using enhanced techniques to try and sweep the remaining oil from trapped parts of the formation back to the producing wells. And again, has had a long history of managing water for production gain. So here in these two scenarios, instead of trying to isolate water completely, it's more a case of managing where you place it and having the injection program tailored to the production profiles that you're seeing. So you're probably looking to find areas of complete watering out and trying to conserve those small areas that have hydrocarbon, maximize their recovery through enhanced sweep or adding new perforations to those areas. So although it's a slightly different situation, it is still about managing that produced water. But again, the criticality is very high in making the right decisions, because with, let's say, only 10% on balance oil production, shutting off just 10% of the water could effectively double your hydrocarbon content. So there's some big gains to be made, but with slightly tighter margins, because you're not as perhaps oil rich as you would have been in earlier fields, you need a cost-effective, simple solution that you can take safe remedial action based on the results. So that's a macroscopic view of some of the main challenges about productivity and profitability and overall production rates. But there are some other associated issues that come with the produced water. And I just wanted to take a few moments to walk through those, because some of you might recognize them, and it may be that these are the issues that you're dealing with on a day-to-day basis with your wells. So first of all, the water isn't exactly pure. In a lot of cases, it will bring with it mineral content held in solution inside the water itself. And as the physical conditions change inside the well, temperatures and pressures change along its transit, these materials and minerals will come out of solution and start to form deposits inside the wellbore. And this can have a significant impact on production, either directly at the perforation tunnels and restricting that contact between the well and the reservoir, limiting the performance of inflow, or potentially further up the well, restricting the transportation area, the inside coatings of the tubulars themselves, and restricting the cross-sectional area available to flow. And a third issue could be that it actually starts to impact the performance of specific downhole hardware, such as pumps, valves, or other production supporting items. And that can result in underperformance or even premature failure, which results then in turn in greater operating expenditure to keep the wells healthy and running. The second issue we might encounter is a different sort of compounds brought along with the water. It could be that you have dissolved oxygen in the water itself, which could feed oxidation and potential corrosion inside the tubulars. Or you may have other gases or compounds in there, such as carbon dioxide, chlorides or sulfides, that can form acids and further attack the completion, limiting and degrading the barrier performance, but also again attacking some of the downhole hardware, causing premature failure, and again that suboptimal performance. And it's not just dissolved content that we need to worry about. In a lot of cases, a breakthrough of water can bring with it free particulates, particularly sand grains and fines, and these can have an incredibly erosive effect on the well itself and some of the surface structures. Or if the flow rate is insignificant or not enough to lift the sand or solids to surface, then they'll accumulate downhole, eventually choking off production and potentially killing the well. So again, it's not just directly the water, but sometimes it can be the associated problems that can cause us headaches as well. But all of these issues, whether it's scaling, corrosion, or solids content, they can be measured and you can take action against them. And with time-lapse data, you can understand if that remediation is being successful, and you can apply it then on a field-wide basis and hopefully deal with the problem by managing the symptoms. But I think it's fair to say, as with all issues, the most direct route, if at all possible, is to eliminate the problem at source. In this case, trying to isolate and reduce the amount of produced water from the outset. So how might we do that? How do we start with the challenge of managing water production? Well, the answer, with many other challenges being similar, is that we use information to drive our decisions. And one of the most common methods of gathering information from wells, looking at their production profile, is through production logging. And there are, of course, many service providers with this technology. It's a very mature method, very well understood, and overall highly successful. And if we look at the two main groups of technologies and services available here, we have what we call centerline production logging tools, the original single sensor inline approach, ideal for commingled flow and very well suited for mixtures of flow inside vertical wells. And these have point sensors measuring statistical changes in physical properties of the fluids with respect to depth or time. But with the advent of highly deviated wells and segregated flow, we needed to supplement that, and the industry came up with array production logging tools. And they simply took the same type of sensors and gave them a greater spatial distribution, placing similar devices in an array, whether it's around the circumference or directly across the wellbore, to try and sample at multiple points and take account for segregated flow. And these work great when the flow is laminar and you have significant volumes of each phase that you're trying to resolve. However, with every system, and there's no real limitation on this, every single system you use does have a limit. It's only so much that it can actually work in terms of its physical environment and specification. And for production logging tools, there are two main issues here. Firstly, that they are point sensors, that you physically have to be sampling and touching and making contact with the thing you're trying to measure, and that those measurements are indirect. You're taking measurements of the properties of that fluid to try and understand what it actually is. It's also a statistical measurement, that you have to rely on a frequency and event happening over time, and that's subject to assumptions in the analysis, although a very mature technique and very well-educated guesses are made in that respect. So don't get me wrong, these are fantastic technologies. We're simply discussing, and we're going to look at situations where they have limits and they have difficulties in providing a clear answer, before we then take a look at a solution that can help bridge those gaps through combination of other technologies. And yes, you've guessed it, that's going to have something to do with video. So to look at those challenging environments, I wanted to look at 3 separate and distinct issues and accompany that with a video clip to show how we might be able to overcome that. The first point I want to make is that those production logging sensors are points of contact, and you need to have that contact with the fluid you're trying to sample. In the same way that your finger can't tell the contents of your coffee cup, whether it's wet, dry, hot or cold, when you're sitting on the other side of the room to your cup. You need to physically place it in there to understand what's going on. If that point of contact isn't made, or it's for too short a time, or the frequency of contact is too low, then the response won't be registered or it'll be undersampled. And in this example, the production logging sensor may have been able to detect the pooling of water that we saw at the end of the video clip, but it might have struggled to resolve the exact location of its origin. Whereas the video, on the other hand, shows the water coming in through a single perforation very, very clearly. If we turn this the other way around, and instead of having a small volume of water and a large volume of gas, we can now look at the reverse. In this case, we're actually running in-hole in a horizontal well in the Gulf of Mexico, and we're about 15,000 feet into the well at this point, so quite a deep intervention. And you can clearly see the hydrocarbon on the high side of the well on the video. And in fact, we chase it down to this sliding sleeve, and that's the final point at which we can see oil inside the well. So we understand immediately where that oil is emanating from, and that underneath that, there is no further hydrocarbon contribution. But again, with such a small volume of oil situated at a remote part of the wellbore, that would be incredibly difficult for even array production logging sensors to sample, either through spatial placement of the sensors or the physical location of the sensors and how they're deployed. And the last point is to do with the complexity of some flow regimes. In this case, we've got bidirectional flow. We have slugging that's occurring, and that can be very difficult to understand. And as an analyst, you need to be able to estimate and understand these flow regimes to apply relative velocities between phases to make your interpretation valid. So this type of flow, where you have both upwards and downwards flow that varies across the cross-section and is varying with respect to time, can be very difficult to resolve. But the video camera sees it immediately and makes it very clear what's happening. So that additional information could be a real aid to the analyst to be able to come up with a valid flow regime and interpretation of the production at this stage. So again, to make that super clear, we are not suggesting that we throw out the old technology, not at all. As we said, very reliable, very much tried and tested. But in the environments where they struggle, what we're suggesting is that we supplement that information with another sensor and a different measurement technique. And if you like, we can call that the video-assisted production log. This is a relatively easy thing to do. And with the combination of the information, the value of that greatly outweighs the incremental cost. If you consider the small cost of adding the camera to the existing program, where you have the wireline crew or the coiled tubing system, you may be managing the well's production over time. Adding a simple additional sensor is relatively small in the scheme of things compared to the information it's going to unlock. The other advantage of it is it's very intuitive and easy to understand. You look at the pictures and you understand immediately what's happening. And you can see those results either in real time in a lot of applications, or certainly at the well site. If you're working in memory mode, you can download and view the video immediately. So what we're going to do next is we're going to look at a couple of short case studies examining the benefits of this in a bit more detail, before then having a look at how we might be able to strengthen the relationship between video and production logging through the emergence of new technologies. So our first case study is an extract from an SBE paper, and I've placed the paper number up here in the top right-hand corner for those that want to make a note of that. And this was written a few years ago, but it documents a scope of work that occurred on land in the US, and it relates to a study about isolating water at source using an injected polymer gel. So in this case, the operator had a solution in mind. The question was where to place it to get maximum effect. But if we study the problem in a bit more detail, there are a few key points that we need to know. So this study actually incorporated a field with several hundreds of wells within a specific basin. And these are unconventional wells with hydraulically fractured shale formations that were being targeted, and we're extracting the oil from those, oil and gas, predominantly gas. But this particular field has the added complexity that the hydrocarbon-bearing shale is situated on top of a water-bearing limestone. And as a result, as the operator started to draw down on these wells, they were rapidly faced with an increasing well count with high water-to-gas ratios. The knock-on effect of that was twofold. Firstly, they had to retrospectively go and fit the water handling facilities. And again, considering the vast areas involved, connecting each well up to the water handling system and increasing the capacity over time to deal with more and more water was proving to be quite a financial burden. And the operator involved estimated that the cost of the water treatment and disposal was somewhere in the region of $6 per produced barrel of oil, which when we're sitting at $40 oil is quite a large part of your margin straight on the outset. But as time went on and the water content became more and more, we had the issue that the hydrostatic forces were starting to overcome the primary pressure drive from the reservoir. So in this instance, the operator then had to retrospectively install artificial lift, which again places another burden on the operating margins. So as part of the study, the operator involved the service company with the polymer gel solution, and they used a combination of production log combined with video surveys to identify the areas of water production. EV were asked to be part of that program, and we supplied video services in memory mode for conveyance on conventional coiled tubing. Those results have been analyzed to find the water-bearing zones, and the same coiled tubing system would be used to inject a localized and targeted remediation using the polymer gel. So let's take a little look at some of the highlights from that scope of work and the information that was provided. So in this first example, you can see the amount of water that we're talking about and the fact it's quite a large volume overall. But if I walk you through the video, you can see the water-gas interface on the high side of the well at around 11 o'clock. And you can see that the gas is flowing along that high side quite nicely. You can also see a presence of produced sand on the low side of the well, something we touched on earlier on with our challenges, and we'll certainly see again later on in this case study. But what you can also see at around the 2 o'clock position is that we have this perforation that we've just repeated the video clip around this area. And you can see that we've got gas coming into this highly water-bearing zone from this single perforation. And there were a few of these. A production logging sensor on its own would have really struggled to resolve that. In fact, it's pretty much impossible. It's too small a hydrocarbon volume inside such a large mass of water. And in a lot of instances, a centerline production logging tool would really fail to understand the presence of the gas flowing on the high side as well. It's just dominated by the surrounding water. But the video provided clear evidence that although there's a lot of standing water in this zone, there are still hydrocarbon-bearing areas, and we wanted to protect those and not unduly isolate this from the production stream. Our second video clip shows the opposite. In this case, we're predominantly inside a gaseous area, but we can see quite a large amount of water being produced from this set of perforations. We can see at the 3 o'clock, the 5 o'clock, the 9 o'clock, and 11 o'clock positions, water pouring in. And we can also see the pooling of water, and the flow of water along the low side of the pipe. So again, the production log may have been able to find some of this flowing water being transported up the well, particularly as we go in and out of changes in inclination. But it would very much struggle to identify the exact location of those perforations because it would probably only have contact for a split second and maybe undersample the result. But by having the two in combination, we could clearly see where the water was, and we can understand potentially its volumes and flow rates from the production log, looking at this in between the stages. So a few different examples there of where the video added value. But if we now turn to the overall results, we can see the impact of that extra information and the use that this gave to the operator concerned. So as part of this study, the operator used 3 different techniques to identify the source of water and the same polymer gel remedial solution in all cases. The first effort was based around a little bit of guesswork by looking at the geology in the surrounding area and the well path itself and its trajectory. The operator took a guess at where the closest proximity between formation and water-bearing limestone would be, and suggesting that the water would break through in those areas. So by blindly shutting off and applying the remedial solution at those locations, they were able to isolate water in 5 out of a total of 12 target wells. So a 42% success rate in actually identifying and shutting off water. But of the 5 wells that they were successful in, they managed to reduce the water production by an average of nearly 70%. So when it did work, it worked very well. The next step was to use conventional production logging data, and this is without video. So it's just regular flow meters and fluid identification tools. And you can see straight away that the success rate is now much higher. We're now at a 2/3 success rate with 10 out of 15 wells successfully identifying and then isolating water. The overall volume of water reduction per well has gone down by a reasonably large amount, which is a little bit counterintuitive, but we'll see in a few moments some of the factors that may have affected that. The video logging technique, in combination with fluid identification sensors, on the other hand, proved to be highly successful. And in this case, we've got a 75% success rate. 6 out of the 8 wells that were attempted, we successfully managed to identify the source and apply remediation to that location. And the best news of all is that we had the greatest reduction in overall produced water. Now, on average, this water reduction is somewhere going from roughly 150 barrels a day down to 20 barrels a day of water production. In return, most wells saw somewhere between a 500,000 scuffs per day baseline up to a 900,000 scuffs per day production thereafter. The exceptional wells were even better than that. And in fact, one of the wells that was attempted, we had up to 98% water reduction. So an incredible success there. Overall, the program was seen as being highly successful. And compared to the conventional technique of squeezing cement into these zones and then milling it out, the cost of using the polymer gel was so much lower that they were able to add an extra 25% of remedial services for the same overall budget. They were also able to reduce the cost of the diagnostic services by approximately 2/3. And that's because we're now using slim, simple centerline tools that would fit through the existing completion and work with great effect. So those two elements in combination gave a fit-for-purpose solution. It had great results and at a lower cost point than the conventional techniques. And again, if you'd like to know any more details of that remedial solution, the paper itself was written by the service company that provided the polymer system, and it talks through the actual content of the system, how it's applied, and typically the sorts of volumes that were pumped. The benefits of this are that rather than a highly viscous material, this is quite a light sealant, and it activates actually out in the fractures itself. So rather than trying to plug off the perforation tunnels or the well bore itself, it's by squeezing it out into the fractures and letting it set in those small tight cavities. That means there's very, very little cleanup and no restriction in production from the rest of the well. There's no need to go in and mill anything out. It's very good in terms of leaving open pathways for future intervention or production from other zones. But we mentioned earlier on about the reduced volume of isolation of water from the production logging sensors. Now, this may be just one of the factors involved, but we mentioned that there was a lot of produced sand in some of these wells. And you can see here, this is one of the more extreme cases where we're pulling out a hole and you can physically see the sand falling back to the low side of the well as we're plowing through it with the video and production logging assembly. Now, the effect of this amount of sand on a traditional flow meter would be pretty much catastrophic. And that was one of the issues that the conventional PLTs suffered from, that although the fluid identification sensors were working to a reasonable standard, it was very difficult to understand the flow rates overall. So there could have been standing water there that was registered, but it wasn't possible to understand if it was moving or if it was stationary. And from that, I think a few assumptions may have been made, and it led to potentially less water being isolated than when you could physically see the points of inflow and understand the static or dynamic behavior of the water in the well. That's just one of the possible reasons. But again, the combination of those fluid hold-up sensors and the video certainly proved to be very effective in this particular case study. Okay, the second case study follows a fairly similar theme, but in this case, this is actually an offshore well, quite a high gas production field that's offshore of the coast of the Netherlands. As with the previous example, this well was experiencing increased water production over time. And in fact, the amount of water being produced was so severe that the column of water and the forces that invoked eroded the natural pressure drive from the formation and ultimately led the well to being shut in due to the amount of water. So again, the operator decided to run a combination of video and production logging sensors to try and understand the exact entry points and origins of the water downhole, to try and then isolate it and regain production. The production log showed areas of interest, and there were some points where you could clearly see elements of water, but it was only really when you looked at the video that you could again see the individual perforations and their exact location to find where the water was coming in for sure. The additional bonus of seeing the video is it identified quite a large presence of scale in the well. So before the solution could be placed into the well, the operator who was planning to run a patch, a straddle, or a plug, depending on the results, they were able to see this scale and perform a cleanup operation to help the seal assemblies provide maximum effect when they were set. So having done that, having found the areas of interest, having cleaned up the areas to accept the straddle, that water-bearing area was isolated and the well was brought back onto production. And I think, as you can see from the graphic, after an initial clean-out period, when the well was lifted and brought back online, you can see that the water had dropped significantly, and we're now back to near original levels of production and pretty much water-free. So again, a great success there, a relatively simple intervention. The challenge was knowing exactly where to place it, and with the added complexity of knowing that you'd have to do some cleanup to make sure the seal elements were working to their maximum effect. So those are the two case studies I wanted to run through, and each of them has their merits, and you can certainly see the success of information converted into action, and that they occur in different types of wells in different locations. But before we close and open up to questions and answers from the audience, I wanted to explore how we might be able to strengthen the relationship between the information provided by video services and production logging surveys. And that's through the application of two new and emerging technologies that EV released to market in the last 12 months. So firstly, we have visual analytics, which is, in simple terms, quantified video images that we can see not only what's happening in its behavior, but we can measure it to understand its severity and impact. And with that, we also have a new camera technology that we call OPTIS Infinity, and how that can be applied to really drive the value of visual analytics. So we'll start with OPTIS Infinity, the new camera technology itself. This has been a number of years in the making, and you can see that it consists of an array camera looking sideways at the pipe wall, and this is the world's first array camera for downhole applications, in combination with a conventional downward-looking camera sensor as well. But if we look at the smart part of the assembly, that's the array itself. We can see 4 identical camera systems aligned at the same point and pointing at 90 degrees facing from each other. Now, those camera systems have an overlapping field of view, so we actually capture a full 360-degree video image of the well without any moving parts inside the tool itself. So with that, we can actually move the system along the axis of the well like a conventional logging tool, capturing high definition, high frame rate video along the way as we go. And we can use this for a number of applications, from looking at scaling, corrosion, or even, in this case, we're going to suggest base holes in screens or perforation in production sections. Just to give you an idea of what that video looked like, we've got a short video clip taken from the tool, the type of thing you would see at the well site on the left-hand side here. I'll just play that video clip again. And you can see all 4 cameras and the full field of view that they get. And you can even see where you have overlapping base holes from this screen view. Like this perforation and base hole here is most likely this one here. And likewise, those 2 there are identical. They are the same item. As we have here and here, here and here, there's an overlap in that field of view, which allows us to see a full 360 degrees. Once we've captured that information, we can then produce this image that we're showing on the right-hand side. This is what we call a mosaic image, and it takes all 4 camera feeds and analyzing the overlap of the areas of interest to produce a continuous 360-degree top to bottom image over the area of interest. So again, a huge amount of detail in this and with no information lost. But once we have that information, we can start to now analyze it. And one of the things we can do is actually start to take measurements of features that we see. And in this case, with this particular screen, you can start to see that there are solids that are formed in these base holes. Now, this could equally be perforations in a conventional well, where you've shot into the formation, and over time, you've had water production. It may have brought with it solids, either freely moving or in suspension, that are now starting to settle in the perforation tunnels themselves. But by looking at the original perforation size and comparing the cross-sectional area that's available for flow, we can now start to understand if these perforations or base holes have been compromised in some way and affect the overall flow and contribution from that zone. So if we imagine this in combination with the production logging survey, where we may have lots of different zones of production and different responses from the flow meters, from the temperature sensors, the fluid identification tools, the production log tells us what fluids are coming in and roughly the proportions of each as we go through each individual stage or section. But if we wanted to analyze in more detail, if there was a particular zone that we were concerned about that may be underperforming, we could take a look at the video clip captured in the same run-in hole, and we could start to look at different trends. This first plot we have here depicts variations along the length of the well and how the solids contribution in those base holes that we saw earlier on in that screen vary as we go deeper into the well. So towards the heel of the well, we had very little solid content blocking those perforations. But as we moved deeper, we actually found that more than 50% of the perforation flowing area was being compromised by the presence of solids. We could even look at trends around the azimuth, looking at the circumference of the well and maybe the orientation and phasing of the perforations. And from these two, we can help to understand if there's a particular mechanism that's affecting performance and potentially advise whether this is something that could be removed. So it could be that if you have hydrocarbons coming in at this zone and you're seeing the presence of solids in the perforation base holes, in the perforation tunnels, you could elect to do a cleanup operation, maybe acidizing, maybe jetting, maybe even electromechanical pulsing, or it could be that you simply go and shoot more perforations in that area, knowing that that will increase the well reservoir contact. And conversely, it may be that you can understand where you shouldn't perform cleanup, where the perforations are unaffected and producing perfectly, or that they're actually producing the fluids you don't want and you can isolate them. So again, this combined set of information could really help to supplement the information provided from a production log with perhaps some of the drivers and mechanisms affecting that inflow performance. So with that, I'll just make a quick note to say that this isn't the only application that we can apply these new technologies. And EV are actively using visual analytics across a range of different operator challenges, everything from corrosion. We looked at sand control. We can look at fishing and how we can measure what we're seeing and help improve the extraction and safe recovery of fish. Wellbore restrictions, possibly deformation related, leaks, valve related issues. There's a whole array of things that we can do because the amount of information we get from video cameras is now phenomenal. And the ability to take those measurements in situ and post-process gives us a much wider array of applications where we can contribute some real knowledge and valuable information. So we hope by looking at the case studies that we've shown and the technologies that drive them, that we've demonstrated how the optimization of water detection and ultimately its isolation can be improved through the combination of video and production logging techniques, and how that can then in turn lead to more effective management decisions and better outcomes, both economically and operationally. So with that, I will conclude my presentation here today, and we'll open the floor to questions and answers from the audience. So Mike, I just want to do a quick check. Have any questions come in through the chat channel whilst we've been speaking here today?
No, nothing yet, but please, if anyone has any questions, you can fire them in chat channel or you can use your mic directly. So we've got one that's coming from Benjamin. Is your camera usually on the same tool string as a PLT?
That's a great question. Thanks, Benjamin. We could do this a number of ways. Yes, we can combine the two. The only concern that we've had when discussing this with the production logging provider is that in a lot of cases, we'll want to put a down view camera at the bottom of the string, and that is by definition a bottom-only device. But as long as you have, let's say, either an inline flow meter a little bit further up, or potentially an array flow meter behind the camera, for a lot of the cases where the video adds value, a full bore or a bottom spinner is not really going to be of great loss from the data set, and the value of the video information overcomes that. So that's one way we can work, and certainly if you're working on coil or slick line and doing memory operations, that's a really simple thing to do. But alternatively, with the array camera, we could position that above the production logging string, looking at the 360-degree images and allowing the production log to work in full underneath, undisturbed. So I hope that's that answers some of it. But if it comes to it, we could do a separate run altogether. We do this sometimes with well integrity surveys. If you've already run a production log or you've run, let's say, a multi-finger caliper survey, we could then come and supplement that with a secondary video log and help combine those two data sets together retrospectively. So either or, but certainly in the same run means you're absolutely comparing like for like under the same conditions.
Yeah, that actually answers the question there, if there was any cases where the camera was run without PLT. So you've covered it there, Tobben. Any more questions, anyone?
Hey, this is George Norton. Question for you. When you were talking about the water shutoff projects, what have you seen, I guess, from kind of all of the studies you've done, not just those specific ones, to kind of be the most successful way of remediating that?
Oh, that's a great question, George. And I'll speak from some of my experience from multiple lives here in different service companies. And I'll actually also turn to my colleagues who may have different experiences and other pearls of wisdom to offer. But it really depends on the situation. I've seen a lot of very successful work in the North Sea, particularly in the Danish sector, where they're producing from carbonate formations, and they are continuously circulating injection water to try and sweep through the carbonate field. In a lot of cases, a simple bridge plug can be the most effective. If you're absolutely certain that you don't have any hydrocarbons coming from the toe of the well below that water entry, then a plug, very reliable, very easy. You can verify its performance very simply with an inflow test, or even actually placing a camera on top of it and looking for bypassing if that's the case. Alternatively, as long as you treat them well, mechanical solutions such as straddles and patches, again, great track record of using them. They just come with that slight downside in some instances that you do lose access to the well below. But again, if that's something you're willing to work with, then fine. The more recent advent of polymer-based sealants or gels, I've seen a number of cases where they've worked tremendously successfully. But in all of these cases, and my history goes back, I had 5 years of doing very specialized leak detection using ultrasound. The companies making the sealants or the remedial solutions, they were our best friends as the diagnostic company, because we helped show them exactly where to place it. If you put any of these in the wrong position, it just simply doesn't work. The device is probably doing what it's meant to be doing, but it's just not at the right location to get maximum effect. So I think it's a bit of a mixed answer, but really, as long as you've got a range of options, it's more a case of narrowing it down and making sure you put it exactly where you want it and where you need it. But I'll open it up. If anyone else from the EV team or even some of the audience assembled, if you've got similar stories to share or differing views that you can add, it'd be great to hear them.
Hi, Tobben. This is Jordan. Hey, I just wanted to add that also when we get into these water cut wells like this, especially when you get up to your 30% range, you actually always get really good video on these. It's very easy. You don't have to really worry about wellbore cleanup, things like that, and that makes your operation go a lot smoother. Just wanted to add that on the operational side.
Great, thanks, Jordan. And George, did that help answer your question?
Yeah, that's good. I just kind of was wondering what your guys' experience was on that. I mean, obviously, location is obviously number one most important thing. So I can see, where various solutions would work, but locating it obviously number one. So yeah.
Yeah, and I think our second case study was also very useful in showing that it's not only exactly where it's coming from, but also the surrounding areas. And I've seen a number of times where we've gone in to find, let's say, a leak or an unwanted inflow, and the primary solution is, well, let's just set a straddle. And then you realize that the surrounding area is close to becoming Swiss cheese. You know, there are so many sites of corrosion or erosion that you've got to actually straddle off quite a large interval in order for this to be effective. So that case where we saw the scale that was forming in the well as a result of the water meant that the operator could prepare and manage, clean up the area of interest and set their straddle with the best possible chance of those seal mechanisms doing the job they're meant to do. So yeah, I think it's a twin benefit in that sense, where you're going to place it and which is the most suitable technique once you've got it there.
Okay, so we've got a two-part question from Ernesto. So firstly, do we have any case studies to identify hydrates plugs in subsea lines or wells? And secondly, most of the case studies are in clear environments. Are there any recommended practices in heavy viscous soil?
Ernesto, thank you. Those are two excellent questions, and I'll take them each in turn. Yes, we do have a number of examples where we've been in and investigated hydrate formations and the issues that they bring. I do have a little clip that's buried in here somewhere, but it's probably not right to show it. And again, with the video, you can see quite clearly where the hydrates have formed. We've even been involved in operations where the operator's gone in with MEG or a similar solvent solution. They've circulated it around, perhaps with jointed pipe or coiled tubing on top of the area of interest, and we've popped in and out to go and have a look at the progress and how that's been eroded. I can actually think of a number of cases in West Africa where we did that in subsea wells, and that was, you know, to great effect, helping to remove that problem and manage the symptoms there. So yeah, it's something I can look at. If we take your details, Ernesto, I'll see if we've got any released case studies on that we can then share with the group as a follow-up action. But certainly that's something we've definitely been involved in. And again, perhaps some of the rest of the EV team might be able to recall and share some of their experiences on that if I could open that up to the floor. No, okay, just me, but that's fine. We'll certainly come back and see if we can help with that particular question. For the second part of the question, looking at the environmental quality, you're absolutely right, and this is the million-dollar question. You know, is the survey going to work? And the biggest limitation we have on the physics of measurement is that we require an optically clean environment. Much like the production logging sensors have limits in what they can do, so too does the video. But to help answer the question, I've actually got a couple of slides here. It's a very common thing we come up against. It's usually the first thing we have to look into. And I'll explain it that there are two main factors we have to consider relating to the well fluids themselves and how we get a good image. You're right that the examples we've shown have been, you know, very clear. However, that's how the well was producing. You know, in some cases you do get incredibly clear environments, and in other cases you have to do a little bit of work to get to those environments. But the two factors we deal with, they're shown here side by side. On the left, first of all, we have issues around pigmentation of the well fluids. Now, in this example, we're showing, and let me just put my laser pen on. We're showing mineral water. I've already mentioned one brand already today, so I'll not mention a second, against a well-known cola brand on the right-hand side. In terms of the level of purity, both are very, very similar. They have hardly any suspended particulates and solids, but the cola has a pigmentation in solution. So when we shine a light on it, it absorbs that light and dissipates it, and we don't then get a returning signal to the camera showing what's on the other side of the liquid. Whereas in the mineral water, we don't have that issue. There's no pigments. The light travels straight through, reflects back, and we can see the target objects. So the analogy here is with gas and water being relatively clear, and potentially the oil being quite heavily affected by pigmentation. But we can manage that. That's not so much an issue. The second challenge we face is that sometimes the well fluids themselves have suspended particles in them, whether it's fines or particulates, or in some cases, these are deliberately put there. You've weighted up a brine with a dissolved solution to try and kill a well or manage a particular situation. And the presence of those particulates can cause a similar issue that the light fails to get to the target object and back again in sufficient quantities for us to see it. But EV are not a technology provider. And this is the difference that we have with other camera companies, that we don't just say, well, here's the camera, here's the manual, good luck, chaps, tell us how you get on. A typical job will start by planning the intervention on paper, and we'll work with you and look at what the well is doing, what it's producing, where it's producing from, and discuss the objectives that you have for the operation, what you need to see and where you need to see it. And our team of operations planners and engineers will come up with a series of scenarios, a program on paper where we'll work through and look at different mitigations and cleanup operations to try and get the maximum quality at the area of interest. That could be circulation of a clean media. It could be bullheading and displacement of the natural phases as they segregate if the well's shut in. Or it could be, as Jordan mentioned earlier on, actually flowing the well to try and encourage clean either water or gas production over the area of interest. So we'll work dynamically at the well site, executing each of these different strategies as we need to. But the key thing here is our success rate as a result is incredibly high. We operate somewhere between 90 and 95% what we'll call data success rate. This is not whether the tool simply switched on or off, or whether we had any lost time due to equipment failure. No, this is whether we managed to get an image that met the operator objective. So more than 9 times out of 10, when we go into a well, we come out with the answers that you like. So that's really a bit of a statement of how we go about it, and it really is through careful planning and careful job execution. Just to round that off, I really also wanted to stress, and Jordan mentioned this, that the presence of oil in a well is not a terminal issue for downhole video. And in combination with the planning procedures that we also have particular techniques and technologies that we use to help prevent oil from fouling and contaminating the camera lens. So here you can see this video clip that as we move through the water phase, we'll eventually go into the oil where the image goes dark. But as soon as we come out the other side into the free gas, the image goes clear again. We haven't ruined the image for the rest of the well. It will very quickly recover and return to normal. And the same is true in the reverse direction, out of the gas, into the oil, and back into the water. And this video will repeat over and over again. So as long as we can work that clean media to the area of interest, as we discussed, we'll be able to get the image at the right place at the right time, and hopefully then solve your problem and give you the answers that you were looking for. So I appreciate, Ernesto, that was quite a long answer, but I hope it was a very complete response. And if there's still any questions, then please just let us know.
We've got a question here from Ryan. He's asking, what is our preferred method of conveyance and why?
That's a great question. I'm just going to slip back up to the very start of the presentation. And in all honesty, I'm not so sure that we mind which conveyance method we work on. But given a lot of the work that we do is understanding complex problems and trying to resolve them and give an answer in real time, the majority of our work is actually conducted on E-line, straightforward monoconductor E-line, because that gives us the ability to see and control the camera in real time. And for safety critical or high stakes operations, that real-time feedback is phenomenally powerful. We can also work on real-time enabled coil tubing. Now, whether it's electrically enabled or fiber optic enabled, we can do that in real time in those media as well. But if you haven't got that on site, if you are working on a more mechanical solution, whether it's production solutions in coil tubing or slickline, we have fantastic memory systems that allow us to get very, very similar, and in some cases, higher quality images using high density memory. And we also touched on it that we've now developed this array camera with the 4 360-degree viewing video systems. That is available in all types of operation. Standalone memory, surface readout, or actually a blend of the two, where we can see images in real time, but we record the full high definition video into a memory controller downhole. So in that sense, we could pretty much run on anything, but the power of real-time communication and feedback, I think really speaks volumes, and that's why we do so much work on electric wireline. Jordan, I'll draw on your experience again there. Is there anything you'd add to that, having witnessed and worked on a number of these operations?
Oh yeah, for sure. Yeah, anytime you can get real time, it's definitely going to be better, especially when you're trying to locate something real time and not trying to wait and tie it back or correlate it later. But early on when we got into this service, I think some of the video you had just shared was from that same kind of era. Originally in the Haynesville, we were running memory PL strings with a memory camera on bottom. So that was back when we could only get like 5 hours of video on memory, but now you can run a tandem OPTIS Infinity and you could get up to 16 hours of video just on memory alone. So yeah, E-line would definitely be preferable, but you can get away with it with slickline, and you just have different challenges like you spoke on, be it a vertical well or horizontal. Vertical is your older wells, like in the Gulf of Mexico shelf. A lot of those have been shut in for a long time. So as long as you can get through that hydrocarbon cap at the top with a surfactant on the lens, normally when you get into that produced fluid underneath it, it's just crystal clear like the mineral water you had shared on the turbidity chart. So yeah, definitely good success with this service, and there's a variety of ways to get it. It's just, and the more time we have to plan, and obviously the better chances and procedure we can come up with multiple contingencies.
Great, thanks, Jordan. Thanks for that. Okay, I'm just looking through to see if there's any other questions we haven't addressed. Mike, was there anything else on the chat channel there?
Yes, we've got a question here from Adisoji. He's asking, apart from identifying the produced fluid sources, is there a way to quantify the downhole rates?
That's a great question. And at the current time, we rely on the supplementary information from the combined production log. In theory, and this is definitely one for the future, not one for right now, we could track fluid movements using the video images. We take enough of them per second that we can see changes in flow. But at the moment, any particular measurements that we make are derived from the production logging sensors. So again, that's the reason that we're stressing the importance of the combination of the two. They complement each other very well, and we have an overlapping capabilities to help overcome some of their shortcomings in isolation.
Okay, thanks. We've got a question here from Azhan. Can the technology help to identify water-producing zones or base holes or perforations within water-filled boreholes, normally at the bottom of a well?
I don't see why not. I guess the challenge is identifying water flow where you have continuous water and then water coming into it. But in a lot of cases, you may not have that static column. As long as you've still got maybe some free gas in there, that should be possible. And I'll also revert that when you do have water into water, where the video may not be able to see exactly that flow, that's when the production logging sensors and flow meters would kick back in. So again, that complement and overlap between the two should be very strong. But I have seen on some videos that where we have jetting coming in, we do see some turbulent effects. So even then, it may be possible from the video that we can see that, especially if it's intermittent oil and water, or water and gas. Then yes, that should be something we could identify.
Okay, and we've got another question here on the limitation of the fluids through which the videos can be captured. Is there any specific fluids where we cannot capture images?
Oh, sorry, another great question, and this is the one area that we must stress. The limitation of video is that we have to have what we would consider an optically clear medium. So by that, we need to control the well fluids so that they either have water or gas with a clarity that we can actually see through. And this is a very common question. So what I'll do is I'll try and help explain that with a couple of quick slides that we put together, and looking at the two main parameters that we have to deal with. Both of them are shown on this slide here. And on the left-hand side, we have the first one, which is about the pigmentation inside the well fluid. Now, here we're showing, I should use another name instead of Evian. I've given them two plugs now already, but let's say this is Perrier without the sparkles. And on the right-hand side, we have Coca-Cola. Now, they are both, in terms of their purity level, very, very similar. Very small amounts of particulates inside them. But they have differences in natural pigmentation, that the cola is dark and the light that we want to transmit is absorbed before it gets to the pipe wall and back again, which limits our ability to take an image. Now, the analogy here would be the difference between oil and gas versus oil and water, let's say. You can see through the gas and you can see through the water, but the pigmentation in the crude oil or even some of the condensates can be high enough that we don't get the light coming back and we then can't take an image. The second factor that we have to deal with is suspended solids inside the well fluid. It may be that we've got a nice, clear, pigment-free medium, but there could be suspended particles, fines, dissolved solids, or even that you've got a brine in there. You've weighted it up with a particular mineral to kill the well. And it's those particulates that, again, absorb and scatter the light. The key thing here, and the reason why EV is so successful, is we don't simply give you a camera and say, good luck, chaps, here's the manual, tell me how you get on. We are not a tool provider in that sense. We're, in fact, a service provider. So what we will typically do is we'll talk to you about the problem that you're having, what you're trying to achieve, and look at the well itself. Help understand what may be coming in, what may be being produced, and the limits that we may have in terms of visibility. And we will then develop a plan. We have very experienced operational engineers and a planning team who will go through different scenarios and mitigations that we can either circulate with a clean fluid, we could bullhead a static column to get it to the right depths and area of interest, or we can actually produce the well and ensure that we have clean produced gas or clean produced water over the area of interest. So we'll work up those scenarios, and when we get to the well, we'll try and execute them in that way, that if we don't get success first time out, then we'll learn what was the issue and we'll apply a different strategy to try and get it done. And the long story short there is that throughout the last 12 months, we performed nearly 1,000 surveys with what we call a data efficiency rate, which is the number of times that we got the images the operator was looking for, that was close to 95%. So better than 9 times out of 10, we met the objectives of the well and the job without any implications or problems. The other 5 to 10% are the scenarios where we cannot get a clean image. We are unable to manipulate the well, and maybe we have too much solids or too much oil. So again, with good preparation and good planning, we should be able to mitigate against that. And most often or not, the reasons that we fail are because the operator chooses not to go through the cleanup program that we've previously agreed. So again, I'll stress for those people that work with us, and there'll be a few nodding around the table. If you follow our instructions, we will better than 9 times out of 10 give you the answer that you need. If you choose not to for some reason, then we may have a different scenario and a negative outcome. So again, a lot of engineering and hard work goes into getting those results, and hopefully we'll give you exactly what you need when you need it. A little bit more on that though. I would say that the presence of oil inside the well is not a terminal issue. We use a special coating on every single one of our cameras that helps to repel the presence of oil. And it's best shown how this works through this short video clip that I've got on screen now. Again, we're in a highly deviated well with segregated flow. We're currently in the produced water at the bottom of the well. And you can see on the high side, a column of oil. And as we move along the well bore, and as the deviation changes, we come out of the water and into the oil, and sure enough, the image goes black. But as soon as we come out the other side into the free gas, the oil is repelled from the lens of the camera using our specialist coatings, and we can see again. This will repeat when we go the other way, back through the oil and into the produced water. So again, if we do have oil in the well, it's not a terminal issue. It's a question of how we manage that and get the right conditions at the area of interest. So I hope with that, we've answered that there will be some circumstances where we cannot get an image. And if it's an absolute no hope situation, we would typically tell you that in advance rather than try the operation. But more than 9 times out of 10, with the right preparation, we can turn a challenge into a success. And that's really the strength and depth of the EV team overall. Okay, Mike, were there any other questions? And I hope that did answer the question in full.
Thanks. We've got a couple tool related questions. Do you centralize the camera while running, and the maximum temperature and preheating for the camera?
Okay, Mike, you broke up a little bit, but I think I got the gist of it. Do we centralize the cameras, and then what are the operating limitations? Okay, first question first. Centralization. It really depends on the application. For the majority of work we do, yes, we centralize the cameras. Being in the middle of the well gives you the most clear picture. It gives you the widest field of view. And particularly if you're looking sideways at the well, it gives you the best viewing angle to see it from. So most of our work is done running simple centralizers and running in the center of the wellbore. But if, on the other hand, you have a particularly difficult situation where the risk of anything protruding from the tool string is a risk, we'll actually run without any centralizers or very, very simple standoffs if required. And examples of this may be if you've got something like a subsurface safety valve, or even a formation isolation valve that you're not sure whether it's fully open, partially closed, and you want to avoid getting stuck in it. We'll run slick, we'll come down through the upper completion, and in real time looking ahead of us to try and avoid any incidents or accidents. And that way we can get to the area of interest with the minimum amount of risk, get typically good pictures as a result, and then pull back out of hole. If we then want to go further and we're happy that the environment is safe, we can put the centralizers back on and continue as planned. So really it's 100% dependent on the application, but in the most part, we will run centralized because it does give us the optimum viewing conditions.
Thanks, Tobben. And just following from that, what is the ideal logging speed best used to capture video, and would there be any risks running the camera on slick?
A great question. And again, I think some of that depends on the application. I'm going to call on my colleagues from around the operations team to back me up on this one. But for the optimum pictures, we recommend somewhere around 15 feet per minute. And particularly with the array camera, that gives us a very consistent 360 degree at a nice consistent speed that most slick line and coiled tubing units can handle. But if any of my colleagues want to interject and maybe offer other scenarios and applications where we can go faster or where we recommend to go slower, then I'll pause and hand over the floor to the team for a second.
No, I think you're right there, Tobin. That it just depends on, I guess, what are the objects you're wanting to look at. You know, if it's sand screens or leak holes, perforations, you can go slightly different speeds just to make sure that you capture everything you need to.
Great, thanks, Steve. Thanks for having me back there. Much appreciated. Good stuff. So for those that don't know Steve, he's our operations manager based out in Kuala Lumpur. And Steve has graduated through from the field all the way through to management. So he's been out there running these systems and helping to plan and prepare those operations for his customers out there in Southeast Asia. So great, thanks for that, Steve. A real source of expertise there. Okay, Mike, any other questions? I think I did see one that just came in. Is this camera running cased hole only? I think for the most part, by the nature of the operations that we do, it is predominantly cased hole, but we have had some applications in open hole environments. And in some cases, looking particularly at fracture networks and what may be coming through them. And there are two particular circumstances I can remember. There was one where we were looking at fractures in an open hole and looking at where water was coming from. So very relevant to this discussion. And we've got some great images of that, showing the water coming in through the rock directly at source. The other adaptation that we can do on this, and again, it's particularly relevant for North America, where they'll do what they call air drilling in vertical wells. We actually adapted the camera to have a series of ultraviolet emitting light sources. And the great thing about that is that as you run down with the camera through the open hole, any of the formations that have hydrocarbon present physically start to glow under the effects of the ultraviolet. So you're coming down through the rock and just seeing black or dark different materials. And then you may hit a shale or a sandstone that has the presence of hydrocarbon, and it starts glowing vividly in front of your eyes. So that information, along with any open hole surveys or previous geological information, can really help you identify exactly the hydrocarbon bearing zones and potentially tailor the final completion design and production strategy there. So I think in short, we're probably 95%, if not more, cased hole, but for the right applications, running in open hole is something we can consider. And again, with no moving parts and slick tools, yeah, we can help package that up for the right environment, I'm sure. Okay, Mike, are there any questions that we haven't captured so far?
Looks like we've covered them all, but I guess just as a final call, if anyone has any last questions, please fire them in the chat channel or use your mic.
Oh, I think actually I did leave one a little short. There was a question about the operating temperatures and pressures. So most of our camera systems 125 degrees Celsius, but we actually have variants of them that we can equip up to 200 degrees Celsius. Those are used quite frequently in HBHT wells, or sometimes even in geothermal applications. So yeah, there's a lot that we can do there. And I think there's even a question from Svetlana about, do we do anything with hydraulic fracturing operations? And yes, actually, there's a whole series of work that we do around optimizing hydraulic fracturing, looking at the erosion and enlargement of perforations where the fracture fluids and the proppant is going through the perforations. that was actually a topic of our one of our previous webinars. So Svetlana, I'll try and find your contact details at the end of this, and we'll try and send you a link to that particular webinar from our website. But absolutely, if you'd like to discuss that in more detail, then we could take that discussion offline. So again, something we're very actively involved in.
Tobben, thank you very much. Just this a small question. Okay, I understand about perforations, but what about during the process of hydraulic fracturing to see where fluid is flowing when we have several intervals open? I think this is not the case. This one is done after fracturing, right? Not during.
Indeed, that's pre and post surveys that we typically perform. It sounds like you have a very different application in mind. So with that, I think it would be really good if we spoke after the meeting about the type of work you're undertaking, and maybe we can discuss solutions and possible scenarios there. That'd be fantastic.
Sure, thank you.
Great, thanks, Svetlana. That's brilliant.